Okay, so today we'll start chapter 2 from section 2.1. Okay. Finally, we are beginning to learn the real thermodynamics. So the title of this chapter is Introduction, the first law, actually. As you remember, we'll learn about 3 different laws of thermodynamics, and in this chapter we'll introduce the first law of thermodynamics. Before we deal with the details about thermodynamics, we need to know many different terms to describe things in thermodynamics. There are several concepts you need to first accept, several concepts you need to define and accept before dealing with the details. Okay? So we'll deal with basic concepts: work, heat, and energy. What are those and how they are defined? And based on those definitions, we can deal with more complicated problems. Okay? After we learn the basic concepts about the thermodynamics, we'll introduce the first law of thermodynamics. What is that, and how scientists have found out about this first law. Okay? And we'll apply that knowledge to various processes including changes, physical changes or chemical changes, etc. That's the goal of this class. Okay? So after introducing several basic concepts, and we'll introduce the first law of thermodynamics. Okay. As I mentioned in the first class of this physical chemistry class, thermodynamics is basically a study about the flow or change of heat, right? A kind of energy, right? So we'll study the static states of matter and how they differ from one another in terms of energetic quantities. Okay? We'll deal with many different types of concepts, basic concepts, and how they are related to each other in terms of energy, different kinds, different forms of energy, etc. Okay? You remember that this field, this study, thermodynamics, started when the Industrial Revolution started, okay? So they could move the train by burning up the fossil fuel, right? They basically changed the chemical energies of fuel to mechanical energies of train, right? They changed the form of energy. And in this thermodynamics class, we want to know quantitatively how those kind of energy change occur. How can we describe those changes? Okay. To do that, we basically first consider the simple systems. As we did in chapter 1, we first consider the perfect gas, ideal gas, and then we move on to the real gas system, right? What are differences between them, and how can we describe the behavior of real gases? Okay. Since this thermodynamics deals with pretty much everything, every changes of energy, it can be applied basically to everything. Heating and cooling, engine efficiencies, batteries, biological energy transfer, etc. If you know well about this field, you can do whatever you want. Okay? Okay, so we can repeat it again, right? Thermodynamics. Thermo means heat, dynamics means change or flow, right? So we'll deal with how a kind of energy changes from one kind to another. For example, everybody knows what energy conversion is, right? You learned it from general physics class, right? If you drop a certain object from the rooftop, it falls down, right? On the rooftop, this object has only potential energy, right? As mgh. As the object falls down, it gains a certain amount of kinetic energy, but it loses the same amount of potential energy. Finally, as it falls down to the ground, potential energy disappears and all the energy is kinetic energy. Also, some part of the energy could be lost by friction or upon collision, like heat, sound, or light whatsoever. Anyhow, in this simple experiment, we can see how energy changes from one kind to another, right? So in this area, we can deal with this kind of problem. How one kind of energy changes to another. Also, we'll deal with how these kind of changes occur from one kind to another, basically the direction of changes. We know that energy changes from potential to kinetic or other type of energy. Okay? And we also want to know the direction of change. If changes occur, what is the direction? Is there a spontaneous direction of energy transfer? Or could we make the direction opposite? Something like that. Okay? We'll deal with this direction of change in chapter 3. Okay? So let's introduce several basic concepts in dealing with thermodynamic problems. First, there is a system. What is system? System is the object or region of interest. System is the thing that we are interested in. It could be anything. It could be engine. It could be piston. It could be gas molecules, whatsoever. We want to know what is happening to the system. Okay? There are surroundings. Surroundings are everything outside of the system in the whole universe. In the whole universe, we have interest in the system, and all the other things except the system is our surroundings. Okay? And the definition of the system is very dependent upon the boundaries between system and the surroundings. If this box is the system, and all the other parts are surroundings, right? There should be boundaries between system and surroundings, okay? And these boundaries have different properties. Okay? So depending on the properties of boundaries, the system can be categorized into 3 different kinds. First is open system. Open system is the system in which matter and energy can go in and out of the system. So basically both matter and energy can go in and out between system and surroundings. That's the open system. Okay? The second kind of the system is closed system. For closed system, only energy can be transferred between system and surroundings. Only energy, not the matter. Matter cannot go in and out of the system for a closed system. Okay? The third kind is isolated system. Isolated system is the system in which none of them, matter nor energy, can go in and out of the system. Okay? So there are 3 different kinds of system. And in this class, we'll mostly deal with closed system or a little bit about isolated system. In other class, in chemical thermodynamics class, in next semester, you will learn about the open system too. Okay? So there are 3 different kinds of systems. Next concepts are work, heat, and energy. What are those? energy is a capacity to do work. If you have energy, you can do something, right? Energy have many different kinds of form, right? Heat energy, chemical energy, potential energy, kinetic energy, etc. Anyhow, whatever the energies are, it is capacity to do work. If you have energy, you can do something. Okay. So let's get back to what this work is. Okay. So there are two different kinds of energy here. First one is work. The second one is heat. Okay. Let's check the definition of these two forms of energy. Work is a form of energy which can transfer in out of a system that is stored in the organized motion of molecules. Okay. On the other hand, heat is a form of energy which can transfer in out of a system that is stored in the random motion of molecules. So you can see the difference between work and heat, right? So both of them are form of energy, but work is stored in the organized motion of molecules. Heat is stored in the random motion of molecules. So work is something like this. If I have this pen, I lift it up from here to here. Okay? I move this pen from here to here. I did work, right? To move all the molecules comprising this pen from this position to this position, right? So this behavior involved organized motion of molecules, right? I moved all the molecules from here, comprising the pen, from here to here. That's the work. Okay, it's very easy, right? So work involves the organized motion of molecules. Okay. On the other hand, heat. You can easily imagine that heat is related to the temperature, right? You remember the definition of temperature in chapter 1, okay? Since heat is related to the temperature, temperature is related to the random motions of molecules, right? If the temperature increases, gas molecules move faster, right? Something like that. So that's why heat is related to the random motion of molecules. As temperature changes, it only changes the speed of the molecules comprising the system. Okay? Right? So there are two different kinds of energy as basic concepts in dealing with thermodynamic problems. Okay? Here shows the thermodynamic definitions of work and heat. It's very similar to the definition that we have just learned in previous slide. Work is kind of energy which involves the organized motion of molecules. Similar definition of work is work could be converted completely into the lifting of a weight in the surroundings. Okay? I mentioned that lifting this pen from here to here is work, right? Because it involves the organized motion of molecules, right? Same. If you do something and if you are not really sure if this is work or heat, you can imagine that if a certain behavior, certain change can be converted into the lifting of a weight, then that change is work. For example, if you have compressed gas inside of a piston, okay, and using that gas which is compressed. Could we do the lifting of a weight? Yes, right? If you let that gas expand against the atmospheric pressure, then you can lift a weight. Okay, then that compressed gas or the expansion of gas can do work, is a form of energy as work. Okay, something like that. So if you have a certain change of energy which can be converted completely into lifting a weight, that is work. Okay. On the other hand, heat, as thermodynamic definition, heat is a form of energy, etc. Heat in its state by virtue of a difference in temperature between the system and its surroundings. I mentioned that heat is related to temperature, right? At high temperature, molecules move faster, right? You can imagine something like this. If you have hot water compared to cold water, hot water could do more work, right? Hot water can be used to do more work, which means that hot water has more energy, right? Compared to cold water, because it is hot. It has high temperature. High temperature, right? So high temperature means more heat energy, okay? So you can now understand the difference between these two forms of energy. If we move on, there's important convention, which is sign conventions for work and for heat. This can be applied to any form of energy, these sign conventions. All you need to remember is that everything you need to focus on the system. Remember what is system, right? System is something that we are interested in. Okay? So if system gets more energy, then the sign convention for that energy, either for work or heat, is positive. Okay? If system loses energy, then the sign is negative. Okay? For example, if work is done by the system on the surroundings, system did some work on the surroundings, okay? Then this amount of energy is lost, right? So work for the system is negative because system lost this amount of energy. On the other hand, if work is done on the system by the surroundings, surroundings did work on the system, then system gained that amount of energy, right? So work is positive. Similarly, if heat is transferred from the system to the surroundings, this amount of energy is lost from the system. Okay? That's why Q system is negative. If heat is transferred to the system from the surroundings, then the sign is positive. Okay? Oh, I forgot to mention that for work we use small alphabet W. For heat we use small alphabet Q. Okay? All right. More about heat. You remember there are three different kinds of boundaries for a system, right? In terms of heat, we can also differentiate two different kinds of system. There is diathermic system and there is a diabatic system. Diathermic system and a diabatic system. Okay. We already have learned about this in chapter 1. Right? Diathermic system is a system in which energy is allowed in and out of in a form of heat. Okay? So diathermic, the boundary for a diathermic system can move energy in and out of the system in the form of heat. On the other hand, a diabatic system is the system in which heat is not allowed in or out. Okay? That's the difference of system in terms of boundary, if that boundary is allowed to transfer heat in and out of the system. Okay? There are two different kinds. Let's see what would happen for both of these systems if something happens, some changes happen. You know what endothermic and exothermic processes are, right? Endothermic process is the process that absorbs heat. In Korean, we call it 흡열 반응. Okay? Exothermic process is opposite, right? The process that releases heat, or 발열 반응. Okay? Let's see an example. What would happen if endothermic process occur in a diathermic container? Diathermic container. Okay? So this is diathermic container here. Okay? And endothermic process occur, a process that absorbs heat. Okay? If endothermic process occurs inside of this system, since this boundary is diathermic, basically it absorbs some amount of heat from the surroundings to the system. Okay? That's why this process decreases temperature of the surroundings, because surroundings lost this amount of heat. Okay? On the other hand, if exothermic process occur in a diathermic container, it increases the temperature of surroundings. Okay? Alright, so far we learned that heat and work are form of energy, right? Here, there is another basic concept, which is called internal energy. Okay. It's a rather abstract concept, but let's see the definition of internal energy. Internal energy is the total energy of a system at any given time, and this total energy comes from the total kinetic and potential energy of molecules which compose the system. Okay. If we have system, for example, it is a container comprising many gas molecules, right? Those gas molecules have kinetic and potential energy, right? And total energy of those total kinetic and potential energy of molecules is called internal energy. Okay? So internal energy, you learn about the definition about internal energy. So if internal energy changes from one amount to another, okay? For example, if energy changes from initial state with energy Ui to a final state with UF, I means initial, F means final, okay? Then you can easily calculate the change in energy as delta U, which is equal to UF minus UI. That's obvious, right? There are a few important properties about this internal energy. The first one is very important. Internal energy is a state function. State function. What is state function? State function is a function that only depends on the current state, not on preparation of the state. Let's consider an easy example. Let's say temperature. If temperature is like 35 degrees C, we know that it is really hot weather, right? Really hot weather. That describes the system the state of the system. It is hot, right? Okay. So the temperature is a state function too, right? Temperature describes the state of a system. Similarly, internal energy is a state function. If a system has a certain amount of internal energy, then we can describe the state about that system. Okay? But that is not depends on the preparation of state, how they are prepared, how the current state is prepared. Okay? Another important property about this internal energy is that internal energy is an extensive property. Okay? There are two different kinds of property: extensive property and intensive property. Okay? So extensive property is property which is dependent upon the amount of matter. So there are many different kinds of physical variables, and some of them depends upon the amount of matter. For example, mass. Mass. The mass of one pen, if you compare that with mass of two pens, mass of two pens are twice bigger, twice larger than the mass of one pen, right? That's why mass is extensive property. Energy is same. Internal energy is an extensive property. Okay. On the other hand, there are several physical variables which are intensive properties. Intensive property is a property that is independent of the amount of matter. For example, temperature. Okay. If the temperature of this pen is like 12 degrees C, and if the temperature of another pen is 12 degrees C, if you combine both of them, it does not increase the temperature, right? Temperature is same, right? Same as 20 degrees C, right? Although the amount of matter increased, the property did not change, right? It's same. That kind of physical variables is called intensive properties. So temperature, pressure, or density are representative examples of intensive properties. Okay? Alright. Molecular interpretation of energy. Okay. When we define internal energy, the internal energy was defined as the total energy comprising the total kinetic and potential energy of molecules inside of the system, right? So that's the molecular interpretation actually. Gas molecules have kinetic energy, 1/2 mv squared, right? Molecules have potential energy, right? You don't really need to memorize this equation anyhow. Kinetic energy, potential energy, if you combine all of them, you can have total energy, total internal energy. Okay? I believe that you guys have learned a little bit about basic concepts about quantum chemistry in general chemistry class, right? I think you'll learn about these in detail in quantum chemistry class, lectured by Professor Hung-Mok Park, maybe later. Okay. One thing that is important about this result is that if you see the result itself, energy here, energy depends on the temperature, right? Yeah. If temperature increases, internal energy increases, because internal energy depends on the kinetic energy of molecules, right? Kinetic energy 1/2 mv squared, right? If temperature increases, it increases the velocity of gas molecules, right? If velocity increases, internal energy increases. That's all. That's all you need to remember about this molecular interpretation of energy. Okay, finally, conservation of energy. This is the first law of thermodynamics. Very simple, right? You have a simple equation. One equation. That's all you need to know. This is the first law of thermodynamics. Very simple. Okay? So let's describe it. Internal energy of a system can be changed. This represents the change of internal energy, right? Internal energy can be changed by two ways, by heat or by work. That's all. This is the first law of thermodynamics, or we call it the conservation of energy. In Korean, as you all know, energy 보존 법칙, right? There are two ways which can change the internal energy, and those two ways are by heat and by work. Heat and work are equivalent ways of changing the energy of a system. That's all. Why this is conservation of energy? Because if a system is completely isolated from its surroundings, if the system is isolated system, you remember isolated system, right? Then no change in the internal energy take place, right? Because between system and surroundings, there would be no flow of matter, no energy, right? Which means that this isolated system, delta U, is equal to 0, right? Energy does not change. Energy is conserved. That's why we call this conservation of energy, or the first law of thermodynamics. Okay? Very simple, right? So this first law of thermodynamics was established by this famous scientist Joule. You know what Joule is, right? The unit of energy. So basically, Joule established the first law of thermodynamics. Okay? So you can read it if you have time. So the first law of thermodynamics, let's recall it again. The equation delta U equal Q plus W is a mathematical statement of the first law of thermodynamics, stating that heat and work are two equivalent ways, form of energies, and are the only ways to change the internal energy of system. And internal energy is conserved in an isolated system. That's all. Okay? And since the universe, the whole universe is isolated system, okay? So the whole universe, delta U, should be equal to 0. For the whole universe, energy is conserved. We are experience many different changes of energy here, right, on the earth. But whatsoever, the whole universe, delta U, is equal to 0. Energy is conserved. That's the fate of us. Okay? Describes the first law of thermodynamics. All right. Actually, there are several ways you can describe or deduce this first law of thermodynamics. It's not that difficult, actually. For example, if the system is a diabatic, you remember a diabatic, right? There is no heat is allowed in and out of a system, right? Then the only way to change the internal energy is through work, right? And since this internal energy is a state function, it does not depend on the path, right? The change only delta U is UF minus UI. It only depends on the initial state and final state. Since delta U is W, work, in an adiabatic system, you can do work to change from initial to final state in many different ways. Whatever the ways are, whatever the paths are, delta U is always same because internal energy is a state function. Okay? This is the case for the adiabatic system. How about which is not adiabatic or diathermic system? Okay? Imagine that our system is not purely adiabatic. Heat can be moved in and out of the system. Then the change in U, the internal energy, may be the same because it is a state function. Okay? But work is different, right? Okay. Let's use the whiteboard. Just a sec. The first law of thermodynamics is just this. Delta U is equal to Q W plus W. Okay. For a diabatic system, delta U is just W because Q is equal to 0, right? And since it is a diabatic system, we usually put AD, a diabatic. But if it is not a diabatic, then we have to use this equation, the first law of thermodynamics, right? Whatever the processes are, diathermic or adiabatic, these two should be same, right? Because internal energy is a state function. Okay? But here we have heat, here we do not. Let's go back to the slide. If, for example, if 42 kilojoule of work is done in a diabatic container, for a diabatic container, this amount of work is same as the change in internal energy, right? However, to achieve the same change of state in a diathermic container, 50 kilojoule of work is required. Okay? For the diabatic container, 42 kilojoule of work is only required, but for diathermic container, 50 kilojoule more work is required because there is heat involved in this process. Okay? Which means that some amount of energy is absorbed by the system. Okay? And that difference Q should be the difference between these two energy, right? Q should be equal to WAD, or diabatic work, minus W, which is equal to minus 8 kilojoule. Okay. Actually, the system is not absorbing the heat, right? 8 kilojoule of heat is lost from the system as heat, okay? And for an adiabatic system, you remember WAD is equal to delta U. Okay? So if you replace this WAD with delta U, you got the first law of thermodynamics. Okay? That's obvious actually, right? Okay, and let's apply this first law of thermodynamics to various processes. There are many different kinds of processes or changes. Okay. Let's introduce some of them. First one is isochoric process. You remember isochore, right? From chapter 1. When we learned about Charles law, right? Isochoric process is a process in which the volume does not change. Delta V is equal to 0. If volume does not change, which means that there is no work, right? There are gas molecules and the volume is same. Then gas does not do anything, right? It does not do any work. And from the first law of thermodynamics, delta U is equal to Q plus W. Since W is 0, delta U is equal to Q. And for isochoric process, since volume is constant, we put V here. Delta U is equal to QV for an isochoric process. Next process is isobaric process. Isobaric, you remember isobar, right? For isobaric process, the pressure is fixed. Pressure is constant. Okay. Then both work and heat exist, so you can use the first law of thermodynamics. Delta U is equal to Q plus W. Okay. Third one we already have learned is a diabatic process. A process in which there is no transfer of heat in and out of the system. So in that case, Q is equal to 0. Actually, not delta Q, it's Q. Since Q is 0, delta U is equal to W. And for an adiabatic process, we usually put AD for diabatic work. Okay. Next one, isothermal process. Isotherm, right? Remember? Isothermal process is the process in which temperature is constant. Delta T is equal to 0. Okay. You remember from the molecular interpretation of internal energy? Internal energy is proportional to the temperature, right? U was equal to like 3RT or something like that, right? If the temperature increases, internal energy increases. They are proportional to each other. Okay. Since delta U is equal to 0, Q plus W is 0, which means that Q is minus W. Okay. Actually, one thing to remember is that delta U is proportional to temperature only for ideal gas. Okay. We'll get back to that point again. Just remember, delta U is proportional to temperature only for an ideal gas. Okay. Lastly, cyclic process. Cyclic process is a process in which have the same initial and final state. We start from here, we go there, and we come back. Like that. Initial and final states are same. Since initial and final states are same, delta U is 0, right? Internal energy is a state function. Okay? Delta U is UF minus UI, should be 0, right? Since delta U is 0 for cycle process, Q is equal to minus W. Okay? So this is the end of section 2.1 and 2. Okay, now we start section 2.3, work and heat. In section 2.1 and 2, we learned about first law of thermodynamics. Delta U is equal to Q plus W. Right? Then there are many different types of processes, many different types of changes. How can we calculate or measure work and heat themselves? We just learned very simple equation. Delta U is Q plus W. That's all. How can you determine W and Q? That's the thing that we want to learn in this section. So for work, we'll consider a simple representative processes, which is expansion process. Expansion is change of volume of gas molecules, right? So it could be either expanded or compressed. Anyway, we'll consider expansion process and we'll calculate the amount of work for various types of processes. And we'll also consider how we can determine, how we can measure the amount of heat. Alright. Let's recall the first law of thermodynamics. Delta U is equal to Q plus W. To describe a certain type of equation mathematically, sometimes it is really easy to do it by using infinitesimal change or differential. Right? If the amount of heat and the amount of work is very small, it is differential dQ and dW that will result in a small amount of change in internal energy, du, right? We got the differential equation, right? Mathematics. Right? If you have the differential equation, if you have certain expression for each of these variables, and finally we do the integration, then we'll get the final result. That's the beauty about this differential equation. Okay? As I mentioned, we'll consider expansion work, process that leads to change of volume of gas, either expansion or compression. Okay? Okay, let's consider expansion work. Let's consider this kind of system. We have gas molecules inside of this piston. There's a lead here, and there is an external pressure PEX. And internal pressure, the pressure of gas molecules, is P. Okay, PX. What we want to calculate is the amount of work which is required to move an object over distance dz against the force of opposing magnitude F. Okay? Basically, what we want to do is we want to move this lead to this direction, upward, over distance dz against this external pressure. How much work should we do to move this piston this distance dz? Okay? The amount of work is force times distance, right? From general physics, okay? dW should be equal to F times dz. Here, we need to put negative sign, minus sign here, because we are doing work against the force of opposing magnitude. Okay? Basically, we are doing work against this external pressure. We are doing work. We want to do work, right? That's why we put minus sign here. So dW is equal to minus F dz. Okay? So for this kind of work, this is the system. Massless, frictionless, rigid, perfectly fitting piston of area A. Okay? External force F is originated from this external pressure PEX, right? And from the definition of pressure, F should be equal to PEX times A area, right? So we put this expression here, then we get dW is equal to minus PEX A dz. Okay? And here we got expression area times distance, A times dz. Area times distance should be volume, right? So this should be equal to dV, volume change. Okay. Finally, what we get is dW is equal to minus PEX dV. If you want to know the amount of work doing expansion, you can simply integrate both sides, right? And we get W, we get this expression. Expansion work is equal to minus integral Pex dv. That's all. This is the result. W is equal to minus Pex dv from initial volume to final volume. Okay. Right. For example, if this is the expansion process, Vf is larger than Vi, then this integration should be positive, and overall the amount of work would be negative, right? Work is negative. If you recall the sign convention about this work, since the system, the gas molecules, did do the expansion, it did work on the surroundings by the system. That's why the sign of work is negative. Okay? So this is very important expression here. And let's calculate the amount of expansion work for various processes. Okay? We start from this expression. Okay? The first one is free expansion. Free expansion is a process in which there is no opposing force. Basically, expansion into vacuum. Okay? We are doing expansion, but there is no opposing force. If there is no opposing force, which means that external pressure is zero, right? If this is zero, W is zero, right? For free expansion work is zero. Simple. Let's skip this part. How about expansion against constant pressure? So the external pressure, Pex, is constant. What if Px is constant? Then, from the general expression for expansion work, Pex can be moved out of this integral, right? W is equal to minus Px integral dv. And this part is just difference between initial and final volume. Very easy, right? Right. If you plot this process, this expansion process against constant pressure as a function of pressure as a function of volume, we'll get this kind of diagram, right? Pressure, external pressure is constant. Volume changes from Vi to Vf. And the amount of expansion work minus Px delta V is equal to this yellow area, right? From this PV diagram, this area corresponds to the amount of work. Okay? So this kind of diagram, to calculate the amount of work, is called indicator diagram. Third process is very complicated actually. Before we calculate the expansion work, we want to introduce a new concept which is called reversible process. Reversible process is a process during which the system is never more than infinitesimally far from equilibrium, and an infinitesimal change in external conditions can reverse the process at any point. Very complicated. Why? Right? Reversal process. What is that? You can imagine this situation. Reversal process is a process in which changes occur. But during the change, the whole system is very close to equilibrium. Very close to equilibrium. We learned about equilibrium, right? Mechanical equilibrium and thermal equilibrium, right? For example, for this expansion process, system and surroundings maintain mechanical equilibrium during expansion. Let's imagine that. It's really not easy to imagine that process because it will be impossible to maintain almost close equilibrium during expansion. Okay? That's why this reversal process is an ideal process. This only exists in our imagination, right? Okay? So reversal process is a change in which the system is always, during the change, is close to equilibrium. Very close, almost close to equilibrium. That's the definition of reversal process. As I mentioned, reversal process cannot be achieved. It's ideal system, right? Ideal process. Okay? But it's very useful in describing the thermodynamic problems. That's why we introduced this process. Since there is a reversal process, there is also irreversible process. Irreversible process is a process which is not reversal process. And irreversible process is the process that we can experience. All the processes, all the changes that we experience are irreversible processes. Okay? This is imagination. This is real. Okay? So, how could we calculate the amount of expansion work during reversible process? That's what we want to know. So, let's imagine that gas expand. And during that expansion, during that change, we are doing reversible expansion. Which means that whole process, all changes are very close to equilibrium during the whole processes. Okay? For gas to expand, external pressure must be smaller than initial gas pressure, right? That's how gas expand, right? But by definition of reversal process, they are very close to each other. External pressure and gas pressure is very close to each other. Although this one is smaller than this, right? Very small, very close. That's why we can express this PEX as P minus dP. dP is very small amount, right? Differential, right? Okay? So from the first general expression for expansion work, we got this expression. We changed PEX to P minus dP. Here PEX is external pressure. Here P is pressure of gas molecules inside the piston. Okay, you need to differentiate from these two, right? Then from this integral, minus P dV plus dP dV. Okay, dP is very small amount. dV is very small amount. If you multiply very small amount together, it will be much more smaller, right? So we can ignore this part. Then what we get is this expression. To calculate the amount of expansion work during reversal process, the amount of work is minus integral P dV. We simply change PEX to P. That's all we need to do. Okay? That's all we need to do. This is the amount of work during reversible expansion. Let's calculate it for a specific example. Isothermal reversible expansion. Okay? You remember what isothermal is, right? Temperature is constant. Okay? And we want to calculate this amount of work for an ideal gas. Actually, ideal gas. Okay? So let's assume that this is ideal gas, and this process is isothermal reversible expansion. Okay? And from this expression, W is equal to minus P dV. P, pressure of gas molecules, would follow the ideal gas law, PV equal nRT, right? So we can change P to nRT over V, right? nRT over V. And since this is isothermal process, T is constant, R is gas constant, N is constant here. So we can easily calculate this integral as minus nRT, natural log Vf over Vi. This is the amount of expansion work during isothermal reversible expansion. Okay? Simple, right? So if this is re-expansion process, if Vf is larger than Vi, then the whole amount of work is negative, right? Same as that we have saw before, right? Because the system does work on the surroundings, losing this amount of energy, right? One thing to note is that for an ideal gas, you remember that for ideal gas, temperature is proportional to internal energy, and temperature is constant, internal energy is constant, right? Which means then since W is negative, Q should be positive, right? Delta U is equal to Q plus W from the first law of thermodynamics, okay? And delta U is equal to 0, and W is negative, which means that Q is positive. Which means that during this isothermal reversible expansion, some amount of energy replenishes the internal energy. Heat is transferred from the surroundings to the system. Okay? Alright, so we calculated the amount of expansion work during several different processes. If you plot this process using indicator diagram, pressure as a function of volume, how can you represent the amount of work? Since this is ideal gas, PV should follow Boyle's law. Remember hyperbola? Okay. And to calculate this expansion work, what we did was integrate P as a function of volume. We integrate P as a function of volume, which means that all of these areas below this hyperbola indicates the amount of expansion work during isothermal reversal process. Okay? It's easy, right? If you compare that with the amount of work during expansion process at constant external pressure, during this process, during isothermal reversal process, they did much more work compared to constant pressure process, right? We'll draw this later, but you can just accept it this time. Maximum work obtained from the system during reversal process. If the process is reversible, you are basically doing maximum amount of work. This is the maximum amount of work that you can get during expansion process. Okay, we'll actually derive this, why this is maximum later. Okay. All right. Finally, now heat. From the first law of thermodynamics, delta U is Q plus W. We did calculation about W, right? How can you determine Q? Okay. How can you determine Q? So, as a differential form, du is equal to dq plus dw, right? And work can be separated into different kinds of work, right? The first one is expansion work that we have calculated so far. There would be other types of work, like electrical work, some other types of work, right? So we separate work into expansion work and other types of work. Okay, let's assume that the process is isochoric process. Volume does not change. If volume does not change, there is no expansion, right? Expansion work is 0. And we also assume that there are no additional work. So dWe is also 0. If there are no works whatsoever, then du is equal to dq. Okay? So, if you integrate this, delta u is equal to q. For isochoric process, for constant volume process, internal energy change is same as heat. If you want to determine heat, you can just determine internal energy change. That's all you need to know. Okay? How can you do it? Experimentally, you can measure the amount of heat easily, actually. For example, for isochoric process, for constant volume process, we can determine the amount of heat using this kind of tool, which is called a diabatic bomb calorimeter. A diabatic means that this whole device is a diabatic. We are doing some chemical reaction here, okay? But the whole system is isolated, thermally isolated from surroundings, okay? Bomb means that we are doing some reaction here, inside of this here. We are doing some reaction inside, and that reaction results in the amount of the change in the amount of heat, right? It could be either endothermic or exothermic, whatever. And it is calorimeter, so basically it measures the amount of heat by measuring the temperature. Okay. So what we do is we do some kind of reaction, and from the reaction, some amount of heat is either observed or released, and we measure it by measuring the temperature change. Okay? And by measuring the temperature change, we can determine the amount of heat observed or released from that process, okay, from the reaction, okay. And there should be some constant, right, relating the amount of heat and temperature change, right? And this amount of heat should be correspond to the amount of internal energy change, right? Very simple. Okay. Alright, here this constant C, which is a coefficient relating the amount of heat and temperature change, is called heat capacity. Okay. Heat capacity is the, as I mentioned, coefficient relating the amount of heat and temperature change. Formally, the definition of heat capacity is the amount of heat required to raise the temperature of the system by 1 Kelvin. As you see here, right? Heat capacity C is Q divided by delta T, right? That's why it has formal definition like this: the amount of heat to increase the temperature of a system by 1 Kelvin. Okay? And heat capacity is an extensive property. That's obvious, right? If you want to increase the temperature of 1 Kelvin of like 100 milliliter of water, if you want to do the same thing for 200 milliliter of water, you have to put twice as much work, right? That's why it is an extensive property. Okay. Since heat capacity is a constant relating to Q and delta T, okay, remember? Okay, let's use the whiteboard here. Just remember that Q is equal to C delta T. Okay, if this is the isochoric process, we can put V here. Okay, and for isochoric process, you remember that Q is equal to delta U, right? So we can determine this heat capacity at constant volume, which is indicated as CV, by this. Or, similarly, we can do the derivative at constant volume. Okay? If internal energy changes as a function of temperature, okay, as shown here in this figure, if internal energy changes as a function of temperature like this, you can easily determine the heat capacity at constant volume as partial derivative of internal energy at a certain point. Okay, very easy. This slope at point A, the slope of point B represents the heat capacity at constant volume. Right? We have learned that heat capacity is an extensive property, right? We can also have intensive heat capacity. For example, if you define molar heat capacity per mole, right, which is denoted as CVM, this one is intensive property, right? Because we divided heat capacity at constant volume by 1 mole, right? So this one is intensive capacity. Similarly, specific heat capacity, which is defined as the heat capacity at constant mass, is also intensive property. Okay. All right. Relating U and T at constant volume, we have already covered all of these. For isochoric process, delta U is equal to CV delta T, which is equal to QV, right? Okay. So, for example, if you supply a certain known amount of heat to the sample, and you measure the temperature using thermometer, and the ratio between the amount of heat and temperature change is the capacity at constant volume. Okay. If you recall the formal definition of heat capacity is defined as the amount of heat required to raise the temperature of a system by 1 Kelvin, right? If a certain system has large heat capacity, means that to change the temperature of that system, we need a large supply of heat, right? If a system has small heat capacity, which means that we need small amount of heat to change the temperature of that system. If the system has infinite heat capacity, which means that to change the temperature of the system, we need infinite amount of energy. Okay. On the other hand, we can say that we supply a certain amount of heat for a system with infinite heat capacity, temperature does not change. That occurs during physical change or phase transition. We'll get back to this point later in chapter 3 or 4, maybe. Okay. All right. So molecular interpretation of heat capacity. As you remember, since delta U, internal energy, was proportional to temperature, right? Internal energy is originated from the total kinetic and potential energy of molecules, right? And it was proportional to the temperature. Okay. So that's the origin, actually, of the heat capacity, right? If you take the partial derivative of internal energy as a function of temperature, we get some constant depending on the situation. Okay, so it's not that important since this molecular interpretation is about quantum mechanics, actually. which is not covered in this class actually. Okay. So this is the end of section 2.4. 이번에는 우리 그 isothermal reversible expansion에 대해서 그 월을 계산했었고 그걸 인디케이터 다이어그램 우리 그렸었는데 조금 이해가 안 될 수 있어가지고 다시 한번 설명을 다른 방식으로 한번 해보도록 하겠습니다. 일단 우리가 reversible process가 뭔지를 이해하는 게 굉장히 어려운데 reversible process라는 게 정의에 따르면 어떤 변화가 일어나는데 변화가 일어나는 데 있어서 그 변화가 일어나는 매 순간순간마다 변화가 일어나는 동안 항상 평형 상태를 거의 근접한 상태로 유지한 상태에서 변화가 일어난다. 그리고 그 변화가 일어날 때 그 변화의 방향을 평형 근처에 있으니까 쉽게 반대 방향으로 바꿀 수가 있다. 이런 상태를 reversible process라고 하는데요. 당연히 우리가 상상 속에서만 상상만 할 수 있는 그런 이상적인 그런 프로세스이고요. 당연히 그런 건 불가능하겠죠. 실질적으로 평형을 거의 근접하게 유지한 상태에서 뭔가 변화를 일으키려면 무한한 시간이 걸리겠죠. 후지무지하게 천천히 한다면 가능하겠지만 실질적으로는 불가능하기 때문에 그래서 우리가 그 익스펜저 월크를 다양한 프로세스에 대해서 계산을 했었는데 다시 한번 계산을 해보죠. 그래서 우리가 어떤 익스펜저 생각하냐면 이런 파란색으로 해야겠네요. 이런 경우 생각해보죠. 말 그대로 익스펜저 목인데 이런 피스톤이 있다고 생각해봅시다. 피스톤이 이렇게 그 뚜껑이 있다고 생각하고 여기다 이제 걸쇠를 걸어놨습니다. 그래서 초기 상태의 기체 압력이 P1 그리고 부피가 V1인 그런 상태라고 가정을 해보죠. 그래서 그걸 어디까지? 이 상태까지 나중 상태인 이거 이 상태까지 익스펜전을 시킨다고 생각을 해보죠. 이 상태에서의 압력은 P2, 부피는 P2라고, V2라고 생각을 해보죠. 이렇게 익스펜전을 하는데 만약에 첫 번째 익스터널 프레셔가 0이라면 간단하게 이건 프리 익스펜전이니까 1도 0이겠죠. 크게 신경을 쓸 필요가 없고요. 근데 두 번째 우리가 당연히 뭐였죠? PEX가 컨스턴트일 때 예를 들면 PEX가 P2라고 생각해보죠. 이건 어떻게 아느냐? 이거랑 똑같은 실험을 하는데 똑같은 피스톤 실험을 하는데 잘 보이나요? 조금 더 크게 하죠. 똑같은 실험을 하는데 걸쇠를 거는 게 아니라 처음 시작을 할 때 요 위에다가 P2만큼에 해당되는 압력의 P2만큼 해당되는 무게를 가진 줄을 올려놓는 거죠. 줄을 올려놔요. 그 다음에 요 밑에 있는 걸쇠를 딱 치우면 여기 P2만큼의 무게에 해당되는 게 올라가 있으니까 내부 압력 P2, 외부 압력 P2에 해당되는 만큼이 서로 같아질 때까지만 팽창하고 딱 멈추겠죠. 그렇죠? 위에서 누르고 있으니까. 물론 뭐 외부 대기 중에 압력 어쩌고 같은 걸 뭐 신경 쓸 수도 있지만 여기서는 이제 대기 압력은 무시하죠. 고려하기 귀찮으니까. 그래서 이렇게 생각하는 거예요. 처음 기체가 P1, V1의 상태였는데 그 위에다가 P2에 해당되는 만큼의 파이널 프레셔인 P2에 해당되는 만큼의 압력을 가진 무게를 가진 줄을 올려놓은 다음에 여기 걸쇠를 딱 치우면 쭉 팽창하다가 P2 내부 압력과 외부 압력이 P2로 서로 같을 때까지 팽창하고 멈추겠죠. 오케이? 그때 1은 앞에서 계산했지만 우리가 마이너스 P2에 V2 마이너스 V1 at constant pressure constant pressure일 때 이렇게 되겠죠? 똑같은 일을 한 번 더 해봅시다. 이번엔 어떻게 하냐면 처음에 시작할 때 줄을 2개 올리죠. 두 개의 줄을 합친 게 P3만큼의 압력에 해당된다고 생각하죠. 그리고 어떻게 하냐면
한 번에 P2로 V2로 가는 게 아니라 궁극적으로 P2 V2로 가는데 궁극적으로 P2 중간에 한 단계를 거치죠. 이 상태에서 이 걸쇠가 걸려 있는데 걸쇠를 딱 풉니다. 딱 풀면 팽창을 하겠죠. 언제까지? 내부 압력이 P3 위에 있는 이 물체의 무게인 P3랑 같아질 때까지. 여기서 P3는 P1과 P2의 중간 정도 되는 값이겠죠. 이런 상태까지 팽창을 하고 그 다음에 요 추를 하나 딱 없애면 하나 남은 P2만큼 해당될 때까지 또 추가적으로 팽창을 하겠죠. 오케이? 이런 경우를 생각을 해보죠. 첫 번째 프로세스를 두 개로 나눠서 인디케이터 다이어를 한번 그려보면 P, V에 대해서 오케이? 처음 시작을 우리가 P1, V1에서 시작을 해서 여기 P2, V2까지 가는데요. 팽창을 하니까 이렇게 갑니다. 이렇게. 아이소더멀 프로세스니까 이제 보일러 법칙을 따라야 되니까 이런 이제 쌍곡선, 하이퍼볼라를 따라가겠죠. 예를 들면 첫 번째 요 P2가 컨스탄트인 경우 그때 일이 얼마였어요? 이만큼이었죠? 수업 시간에 그 전 강의에서 얘기한 것처럼 이만큼인데 이렇게 나눠서 어떻게 되나요? 나눠서 일을 하면 처음 일에 어떻게 될까요? 첫 번째 한 프로세스 여기서의 일을 하고 여기서의 일을 합쳐줘야겠죠? 첫 번째에서 한 일은 어떻게 돼요? 외부 압력이 P3로 일정한 상태에서 일은 외부 압력이 P3로 일정한 상태에서 V3랑 V1의 차이 이렇게 더하기 외부 압력이 P2로 일정한 상태에서 V2랑 V3랑의 차이 이걸 다 더해줘야겠죠? 그걸 요 인디케이터 다이어그램에 표시를 하면 어떻게 될까요? P3, V3는 뭐 어디쯤 중간쯤 있겠죠? 이렇게 되겠죠? 요 부분의 면적과 요 부분의 면적의 합이 되겠죠? 이렇게 두 개로 나누면 오케이? 이 똑같은 일을 어떻게 하냐면 추 대신에 모래를 올리는 거예요. 모래알을 모래알이니까 무지하게 많겠죠. 모래알을 무지하게 올린 다음에 모래알을 하나씩 빼는 거예요. 하나 뺄 때마다의 그때 일들을 다 더하는 거죠. 언제까지? 이 상태까지. 모래알이 P2만큼 남아있을 때, P2는 놔두고, 예를 들면 추 하나 놔두고, 거기다 모래알을 덮는 거죠, 모래알. 그래서 모래알을 하나 빼는 거예요. 그때마다 하나씩 뺄 때마다 외부 압력이 조금씩 떨어질 거 아니에요? 떨어지겠죠? 그래서 그 떨어질 때의 일들을 다 더하면 어떻게 될까요? 이거가 조금 작을 때의 일. 조금 더 작을 때. 그걸 다 더한 값이 되겠죠? 그럼 결과적으로 요 곡선, 하이퍼볼라의 밑에 전체 면적에 해당이 되겠죠? 그게 뭐예요? 리버시블 프로세스죠? 모래알 하나하나 빼는 거는 거의 평형을 유지한 상태에서 우리가 팽창을 시키는 거죠. 오케이? 그렇기 때문에 그거는 그냥 리버시블 프로세스랑 실제로 같겠죠. 그래서 왜 리버시블 프로세스일 때 요 인디케이터 다이어그램에서 요 곡선 밑에 전체 면적이 그 일에 해당이 되는지를 이런 식으로 우리가 간단하게 이해를 할 수가 있죠. 오케이? 네. Okay. Let's move on to the section 2.5 and 6. In previous sections, we dealt with mainly constant volume process or isochoric process in which volume is constant or volume does not change during the process. So for isochoric process, we could determine the amount of heat during the process. But isochoric process is not really common. Let's imagine our daily lives or chemical processes whatsoever. constant volume process is not common. If something happens to, especially to gas molecules, it usually changes volume, right? On the other hand, isobaric process or constant pressure process is much more common compared to constant volume process. Then for isobaric process, how can you determine the amount of heat? You can do the same thing. You can do the same processes as we did for isochoric process. And for isobaric process, we need new physical variables, which is called enthalpy, which actually correspond to the amount of heat during isobaric process. Okay, so we'll introduce what enthalpies are, definition, how can we measure it, how they change as a function of temperature, etc. And finally, in this section, we'll consider a diabatic change, which is a bit different from other types of changes, other types of thermal, isobaric, or isochoric processes. So we'll consider these diabatic changes, how they are different. So as I mentioned, it's not really common to encounter isochoric process. On the other hand, isobaric process is much more common, and the amount of heat supplied to a system at a constant pressure during isobaric process is actually same as a new physical variable called enthalpy, or large capital H. Okay. We'll derive it actually, but delta H is equal to amount of heat Q at constant pressure, QP. Okay. And interestingly, there is a definition for enthalpy H. H is defined as U plus PV. That's the just formal definition of enthalpy. Why? Why delta H is equal to Q during isobaric process? It's very easy to actually derive it. From the first law of thermodynamics, everything is actually from the first law of thermodynamics. From the definition of enthalpy H, H is equal to U plus PV. We assume infinitesimal changes in state of a system. If U changes to a small amount, U plus du. If P changes small amount, P plus dP. If V changes small amount, V plus dV. Then these small changes would result in small change in enthalpy, H plus dH, right? Okay, if you take all these variables out, U plus du plus PV, PdV, VdP plus dPdV, okay. As we did for expansion work, the PdV, multiplication of very small amount, is really small. So we ignore this. We can ignore it. And by definition, H is equal to U plus PV. H is equal to U plus PV. So we can remove these three variables. Okay? Then what we get is dH is equal to du plus PdV plus VdP. And from the first law of thermodynamics, du is equal to dq plus dw. Okay? So we put this expression here, and we get this, right? dH is equal to dq plus dw plus pdv plus vdp. And let's say that the system is in mechanical equilibrium with surroundings at constant P. We assume it. And there is only expansion work. We are ignoring other types of work. If they are in equilibrium, and if there is only expansion work, dW should be equal to minus PdV. Remember, when we dealt with reversible expansion work, right? So here dW is equal to minus PdV. Minus PdV plus PdV. You can remove both of them. And finally we get dH is equal to dQ plus VdP. And we assume that this whole process is at constant pressure, isobaric process. dP is equal to 0. Then dH is dQ, right? The amount of heat during isobaric process is same as enthalpy change. Okay? Okay? So, it's very simple, right? How can you measure delta H? Or how can you measure Q at constant pressure, QP, Q sub P? We use similar tools as we used for a diabetic bomb calorimeter. This one is called a diabetic flame calorimeter. Pretty much same, actually. Whole system is a diabetic, and we have some flame. We are doing some reaction. The main difference between a diabetic bomb calorimeter and a diabetic flame calorimeter is that a diabetic bomb calorimeter was totally totally banned from the surroundings because the volume was constant, right? Well, in this case, pressure is constant because whole system is open to air. It is open. It is open to atmospheric pressure. So the pressure is constant, at constant pressure. So basically at constant pressure, we are doing some reaction inside of this, and we do the same measurement of temperature, and we can determine the amount of heat, which is equal to delta H, right? It's pretty much same as we did before, right? What is this? This is just an example. An example of how can you determine delta H for a gas, especially ideal gas. Let's look. You guys can read this slide or textbook. Okay, since delta H, let's use the whiteboard just a little while. Since for isobaric process, delta H is equal to QP, which can be determined by measuring temperature. Okay, there should be a coefficient C. Okay, here, since it is isobaric process, we can put here C, P. We can put P. So by measuring heat, measuring temperature, we can determine this one. Or by, if you know the information about how enthalpy changes as a function of temperature, we can easily get Cp. Cp is delta H over delta T, or similarly, we can determine it as partial derivative of enthalpy as a function of temperature at constant pressure. Okay? It is shown here in this slide. Okay. Alright. So, heat capacity at constant pressure can be determined if we know the information about how enthalpy changes as a function of temperature. So we take the partial derivative of enthalpy as a function of temperature at constant pressure. That's the heat capacity at constant pressure. Alright. So we learned about heat capacity at constant volume, CV, and also CP, heat capacity at constant pressure. One thing to note is that this part, So here, let's compare constant volume process and constant pressure process. During constant volume process, okay, there is no expansion, right? So all the heat corresponds to the change of internal energy, right? But at constant pressure process, if the system does expansion, okay, during expansion, okay, they do work on the surroundings. So even we heat the system does work on the surroundings, means that they lose internal energy. Okay, which means that if you supply same amount of heat to both systems, to constant volume system, to constant pressure system, for constant pressure system, the amount of internal energy change is smaller, right? Because this system lost some amount of energy as work on the surroundings. Okay? So even though we supply same amount of heat, temperature of a system rise less when heating at constant pressure. Okay? Right? Which means that heat capacity at constant pressure is larger than heat capacity at constant volume. Let's review the formal definition of heat capacity. The definition of heat capacity is the amount of heat required to raise a system by 1 Kelvin, right? Okay? For constant pressure system, temperature rises less. That's why Cp is larger than Cv. Okay? Especially for ideal gas, this difference corresponds to Nr. And we'll derive this later. Cp minus Cv is equal to Nr. Okay? Finally, section 2.6. How about adiabatic change? We considered isochoric process, isobaric process, isothermal process, all of them. How about adiabatic process? What's the difference? How can you determine the amount of heat or work during a adiabatic process? So, let's see. What changes occur when a gas expands adiabatically? A diabatic process means there is no heat transfer. So from the first law of thermodynamics, delta U is equal to Q plus W. Q is 0, so delta U is equal to W, right? So during expansion, work is done. System does work on the surroundings, so internal energy decreases. Temperature decreases, right? Temperature of the gas molecules decreases. Kinetic energy decreases, which means that average speed of gas molecules gets smaller, right? So, if you put this adiabatic process into diagram, temperature as a function of volume, as volume increases, as we do expansion, temperature decreases, right? This is the adiabatic change. Okay? So, during these adiabatic changes, how can you determine change in internal energy? Or we learn that temperature would fall. How much? How much temperature drops, right? We want to calculate it. So, let's say that we start from here, initial state, to final state. Initial state has temperature of Ti, volume of Vi, final state, Tf and Vf. And we want to calculate first delta U internal energy change during this adiabatic process, adiabatic expansion. Calculating delta U directly following this process is impossible. Actually, not impossible, but it's a little bit more complicated. Okay? One thing good about internal energy is that internal energy is a state function. If you want to calculate delta U from here to here, you do not need to follow this path. You can follow any path whatsoever because initial and final states are same. Okay? So instead of following this line, you just follow these simple lines. Okay? And you calculate delta U. First, this process, constant temperature process. During constant temperature process, delta U does not change for ideal gas. We are basically assuming ideal gas. Okay? For whole semester actually, in most cases we are assuming ideal gas. Delta U is constant. You don't need to worry about. How about this process? Constant volume process. During constant volume process, delta U is equal to CV delta T. Simple, right? Delta U during adiabatic expansion is equal to CV delta T. That's all. And delta U during adiabatic expansion is same as work. So the amount of work corresponds to CV delta T. Wow. Done. Okay? All you need to know is what is delta T. How much temperature drop occurs. We can also do the calculation for delta T, right? Actually, as a result, let's first see the result here. During adiabatic expansion, we want to calculate the temperature change. If you know the information about initial and final temperature, initial and final volume, we can calculate the final temperature if you know initial temperature and initial and final volume using this equation. And here, small letter C corresponds to CVM over R, molar heat capacity at constant volume divided by gas constant. So using this equation, we can calculate the final temperature during adiabatic expansion. Why? Why this equation? How can you get that equation? Let's derive it. All right. Okay. Let's do the derivation. It's not that difficult actually. So, during a diabatic process, what we got was like this. Delta U is equal to CV delta T, right? To calculate this, all you need to know is this, okay? So if you write it in differential form, du is equal to CV dt, right? Okay. And du was equal to dw since it is a diabatic process, right? And we assume a reversible process. We are assuming a reversible process. For reversible process, dw is equal to p dv. Remember, right? Okay. For reversal process, dw is equal to minus p dv. Okay. So using this equation, you can calculate it. So, as I mentioned, we are basically assuming ideal gas. So minus p dv corresponds to minus V N R T dV. Okay? Since we have derivative of T, we move this T over that side. So T CV dt is equal to minus V of N R dV. Okay? If you integrate both sides, CV dt is equal to minus NR 1 over V dV. Okay? Then you can get, if you do the integration on both sides, you can easily get this equation. Okay? You can easily get this expression. If you know the information about initial temperature, initial and final volume, you can easily get final temperature during a diabatic expansion. Alright. Lastly, you remember that for isothermal reversible process, actually it doesn't need to be reversible. For isothermal process, PV is constant. Boyle's law, right? PV is constant. But for a diabatic reversible expanding process, PV over gamma is constant. What? Not PV. For Boyle's law, PV should be constant, right? But for a diabatic reversible process, PV over gamma is constant. Here, the constant gamma is heat capacity ratio between heat capacity at constant volume and heat capacity at constant pressure and heat capacity at constant volume. Interesting, right? So for a diabatic process, or diabatic reversible process, this expression holds. Why? The derivation is actually very simple. Let's do the derivation. It's actually very simple. Okay. Let's first delete the whiteboard. That's so clean. Alright. Actually, from previous slide, to determine the final temperature during a diabatic process, what we got was this expression Ti Tf is equal to Vf Vi 1 over C. Okay? And this is ideal gas, so it should follow ideal gas law. PV equal nRT. Okay? We can express this in this way. If initial pressure is Pi, initial volume is Vi, initial temperature is Ti, something like that, then Pi Vi over Ti should be equal to nR, which is constant, right? Constant, which should correspond to PF, VF, and TF, right? Okay? Similarly, we can express it as PI, VI over PF, VF is equal to TI, TF. And if you put this equation here, you can easily get PV gamma is constant. You can do the derivation by yourself. Okay? It's not really difficult. It's actually very easy. Okay? So, for a diabetic reversible process, this relation holds. Okay? So that's the end of section 2.6.